Welcome to Project 2.7, the Jump Height Tracker. This project uses three main components along with code to track the height of a person's jump. The three main components are the NFP LCD screen, the MPU6050, and the Arduino Nano. Our first component is the NFP131545A, an alphanumeric LCD screen. This 20x4 display allows us to showcase up to 80 characters with 4 rows of 20 characters. It uses I2C communication, which makes connecting and programming simple. This display is powered by 5 volts and it communicates through an I2C address, allowing it to seamlessly interface with microcontrollers such as the Arduino Nano. I2C is a 2-wire communication protocol widely used in electronics. I2C allows multiple devices like sensors and displays to share the same data bus, keeping wiring simple and organized. The two wires in I2C are the serial data line, or SDA, and the serial clock line, or SCL. The SDA line carries the data, while the SCL line provides the clock signal that synchronizes the data transfer in I2C communication. Each device on the bus is assigned a unique address, allowing efficient data transfer. The next component is the main component of this project, the Adafruit MPU6050. This sensor offers both a 3-axis accelerometer and a 3-axis gyroscope. The accelerometer measures acceleration across 3 axes: X, Y, and Z. The X-axis measures movement left to right, the Y-axis measures movement up and down, and the Z-axis measures movement along the vertical plane, or the axis pointing towards and away from the user, capturing the acceleration as you jump. This sudden change in acceleration helps the system detect when the jump starts and ends. Now the 3-axis gyroscope, which measures rotational motion. This gyroscope isn't directly used in this project, but it's still an important part of the sensor. It measures angular velocity, which is the speed of rotation around the 3-axis. In many applications, this is crucial, especially for detecting orientation or rotation. The MPU6050 uses something called MEMS technology, which stands for Microelectromechanical Systems Technology. This technology involves a tiny proof mass that is suspended by microscale springs inside the sensor. When a force is applied, like a jump, the mass moves, altering the capacitance between it and nearby fixed electrons. This change in capacitance is then converted into an analog voltage. The sensor's onboard analog to digital converter, or ADC, digitizes the signal, making it ready for use by the Arduino Nano. So when the sensor detects a jump, the change in capacitance from the movement is processed into a data signal that the Arduino Nano reads and interprets. This efficient technology gives the MPU6050 the ability to provide precise motion measurements in real time. In this circuit, the MPU6050 is connected to the Arduino Nano using I2C. The LCD is also connected to the same I2C bus, meaning they both share the SDA and SCL lines. Powering both devices through the Arduino's 5-volt pin ensures everything is working smoothly. In this code, several key libraries are used to interface with the hardware and manage data. The wire.h library facilitates I2C communication between the Arduino and external components like the MPU6050 sensor. The Adafruit MPU6050.h library allows for easy interaction with the MPU6050 accelerometer, enabling the collection of sensor data. The Adafruit sensor.h library provides a consistent interface for accessing sensor data, ensuring compatibility across different sensors. Finally, the liquid crystal I2C.h library is used to control an LCD display, allowing the Arduino to show real-time data like acceleration values and calculated jump height. Next, some important chunks of code within my code. This first box of code ensures that the MPU6050 is connected and functioning. If not, it stops the program and alerts the user. This next line of code sets a 50 millisecond update interval for capturing sensor data, ensuring consistent and timely measurements. Finally, the last chunk of code detects when a jump ends and then calculates the jump height using a kinematic formula based on the air time of the jump. To make this project even more compact and professional, a custom PCB was designed using EasyEDA. After searching for every part, connecting every pin to the correct place, and checking for errors in the schematic, I created the PCB layout, ensuring everything fits perfectly. Once the PCB was laid out correctly with proper connections, dimensions, and components, I ordered the PCB for fabrication using JLC PCB. Then I designed a custom 3D printed case using Fusion 360. The case keeps everything secure, durable, and easy to assemble. After receiving the case and the PCB, I soldered all of the components to the PCB and then put the PCB into the case. This project taught me valuable lessons in electronics, sensor integration, and coding, highlighting many new concepts within coding as well as new hardware skills such as I2C communication and controlling sensor data.